You can go ahead.
Okay.
There we go.
I'll be back.
This is our Society and Life Training Club. So usually we like to just ask people about their careers, and so we can like learn about the job markets and the different things that we can do with our education. So usually we like to start off our interviews with asking like your high school background and what you did in college and anything you did that you thought was helpful that would help you now in your job.
Sure. Am I just talking to you, or are there other people?
Oh, there are other people. They're in this room.
Like we're around
I
us.
see. Okay, you guys are all hiding back there.
Yeah.
We're just,
Well, let's see. In high school, I took a electronic circuits class, and that got me interested in electronics in general. So I was planning to go into either physics or electrical engineering. And then as a freshman in college, my first year, I took a Fortran programming class, and I really liked the idea of being able to write software and make computers do things, draw things or whatever. So I switched to computer engineering and sort of stuck with that. And most of what I did in college was computer engineering. So I did a little bit of hardware and a little bit of software, not real deep into EE, which would have been like transistor chemistry and transistor physics, not real deep into the standard computer science curriculum. So I didn't do the deep statistics or linear algebra stuff. I mean, I sort of did some of that, but see, this was in the early 80s, so the internet was not well known. There was the ARPANET that we sort of knew about. We were using mainframe computers at the University of Illinois where I was. And then my first job, I learned how to put in a local area network and found out about the internet. This was about 1983. And then I saw in the newspaper in Champaign-Urbana a picture of a Cray supercomputer going in on campus. And so I put in my application to switch over to the University of Illinois and started, that was when the Supercomputer Center started there. So, and then from there, internet stuff and high performance computing, and just kind of went from one interesting thing to another.
Okay, that's cool. So obviously you've worked with like computers for a long time. So how would you say they've like evolved over time, and how like people reacted with them?
Well, I guess what I've seen over time is computers go from being this esoteric thing that happens in the back room to being invisible every day in people's lives, where we don't really think about how powerful our smartphones are, for example. I assume most of you guys carry some form of a smartphone.
Yeah.
yeah.
So that smartphone, this is an iPhone 7. So this is less than $1,000, but it's about 1,000 times more powerful than the first supercomputers 30 years ago. And those computers cost $15 to $20 million. So this exponential change over time in computing, it means that when you're doing research like you are now, or doing a project, you can think about things that are completely unrealistic today that might actually be feasible within 5 years or so. So as an example, the first graphical web browser, when I was at the Supercomputer Center, NCSA, some of our team built the Mosaic browser. And at the time, entire campuses like the University of Illinois had a total internet speed or capacity of 1.5 megabits per second, which you would like, if you had that for yourself at home, you would like barf, it'd be so slow, right? But that was the whole campus had shared 1.5 megabits per second. And at one time I said to the Mosaic guys, I said, are you sure you want to embed images in web pages because it's going to really slow down? And they said, well, we're designing for a time in the not too distant future where the campus has 45 megabits per second, which would also be, that's reasonably good for a home network now, but not for a whole campus. So, and all through, the kind of projects that I worked on, we would shoot for things that it would be very expensive to do today, but would be cheap to do in, say, 5 years. So we would develop software like data visualization software on $50,000 workstations, knowing that within 5 to 10 years, the same power would be available in a PC for $2,000. So we would develop the software and then it would be ready by the time a PC was there. Whereas if you wait for the technology, you run the risk of developing technology that, it's maybe aimed at today, but nobody's interested in using it in 5 years because it's not ambitious enough.
So going off that question, I just wanted to ask, how difficult is it to keep up with all this change? What are your experiences in just adapting to new technologies?
It is. So it's, in some ways it's easy, in some ways it's hard. When it comes to general change of how things are done, for me, it's just a constant. I'm always reading papers. I'm always reading news articles, going to conferences and watching what people can do. So it's fairly easy for me to keep up intellectually. What is difficult, I think, for every human being is when the mechanics of accessing information sort of arbitrarily changes. So as an example, if you try to teach somebody that's like 60 years or 70 or 80 years old how to use an iPad, it's very difficult for them because it's a new kind of interface that they've never dealt with before. They've always dealt with a keyboard. And even myself, like my kids play PlayStation and Xbox 360, and I've never learned how to use that controller. So when I go into a game, I'm sort of like, mentally challenged person walking around bumping into things. I can't even go up a ladder without falling off because I haven't gotten used to the mechanics of controlling. So there's a set of things that you do every day, like interact with a computer, that is maybe hard to adapt over time. So you see people like myself still using the same text editor that I used 20 years ago because I don't really want to relearn that mechanical thing. But where it doesn't have to do with the way we interact, I think if you keep at it, you can continue to learn. And I think a key to it is, like, if it's something you're really interested in. So if you were to decide to go into computer engineering because you thought that the job market was good, or you could meet interesting people or whatever, then you might find it hard to keep up because it's not the thing that you're interested in. Whereas if you go into it because you totally get into you're really interested in it, then it becomes something that you do because you're interested. So when I go home, on a weekend, I might be down in the basement building a sensor to solve some problem at home because to me that's fun. Or I might be doing a Coursera course on machine learning or something because I want to stay current and I'm interested in that area.
Okay. There's a lot of people here who we're all going to college in a few months. So a lot of people have applied to computer science majors. So what would you say is a good, aside from just pursuing what they want to do, what would you say is a good goal for people to have trying to get into this industry?
Well, one thing that we're seeing just in the last couple of years really kind of explode is artificial intelligence. So things like machine learning or deep learning. We're seeing it not just explode in popularity, which is one thing, but in all of the projects that we do where we're doing computational science with physics or chemistry or operations research or urban systems, machine learning keeps coming in as a new capability. And part of that's because the the software and the algorithms have evolved over the last few years in a really interesting way. And part of it's because the hardware that supports that kind of computation has gotten very powerful, and in part because of the hardware that companies like NVIDIA or Intel have had to build to support gaming. So like 5 years ago, for example, people that we were working with, we started talking about the use of gaming systems like the PS2 or the Xbox as computational systems. And it seemed kind of weird that you would use a gaming system to do computation, but the kind of math that you have to do for gaming turns out to be really, really good to support the machine learning algorithms that create neural networks and compute them and that sort of thing. So I would encourage people to, if not go into machine learning and applied math, to make sure that you're well grounded there.
Okay, so just to reiterate, you would say that is that any different from how it was before, where more things were involved? You said like there was physics and other fields of study, or is that more so than it was before, or how does that change?
I'm not sure. So when I was an undergraduate, a software degree would be a very general sort of thing that you learn sorting algorithms and other things. And of course you have to do that, but you have an opportunity to specialize. And so if you're wanting to go in the software direction, then applied math and machine learning is a good way to go. If you want to go in the hardware direction, then I think it's also the case that you want to look at some of these new architectures like NVIDIA's graphic processing units or GPUs. I think the other thing to think about from a hardware point of view is we're looking at new models for computing, because one of the changes that we're seeing now is for my whole career, we've talked about Moore's Law. So Moore's Law, which was coined like 45, 50 years ago, simply says that as we get better and better semiconductor processing and building capabilities, we can expect that the cost of a certain amount of computing will go down every 12 to 18 months by half. Or looked at another way, for the same amount of money, you get 1.5 to 2 times as much computing power or memory size over an 18-month period of time. So that's why the iPhone can be 1,000 times faster at $1,000 than a $15 million supercomputer was 30 years ago, because it's an exponential growth. And that seems to be slowing down just because of the physics of building chips. We're starting to reach the limit. So when you think about hardware architecture, then something, what you might have thought about 10 years ago would be things like instruction sets and reduced instruction sets and different ways to organize the CPU. Now what you might think about is quantum computing. You might think about neuromorphic computing, or even biological-based computing, like based on DNA. So from a hardware point of view, things have opened up quite a bit. So you might find yourself with an interest in biology, applying, doing like a biology/computer science degree, looking at the architecture that you might build if you could harness the storage power of DNA.
Okay, that's interesting. Does anyone have any questions?
So can you describe, like, from a day-to-day basis, what are the type of things you work on?
Sure. I'll tell you what I work on, and then I'll tell you what people that work for me work on. Okay. So the people that work for me, we're doing a couple of projects right now. So one is called the Array of Things. It's this thing here. So this has got, we had to design this. It's got computers in here. It's got a bunch of sensors in here. It's got camera here, camera there. It goes on a pole like that. And so there's a bunch of guys that work for me, and women, that are working on everything from the software that runs inside here to the hardware interfaces and designing circuit boards, to start out with an idea, which was, can we put something up on a pole that can do different kinds of sensors, that can do image and sound processing right down in here, so we could run machine learning code right inside here. So there's a bit of electronics design where you have to really understand how circuits work and how to power computer circuits in a way that doesn't fry them and yet gives them enough power to actually operate reliably. And there's mechanical design, and this is an injection molded set of parts here, and so we've had to work with people on industry design, and this is all sort of custom stuff. So some of the guys working for me on a day-to-day basis are like building and debugging circuits, and then right next to them, and sometimes it's the same people, are working on the software that runs on that platform. And how does the software running on that platform talk over the internet to the sort of mothership, the database that we're sending all the sensor data to? And then how do you update software out there and manage it sort of locally? So there's a lot of programming involved. A lot of it's using Python or C++ or other things. And then I have some people that are looking at the data. So in that box I just showed you, there are 5 different temperature sensors, and they're all different technologies that you use to measure temperature. So we want to be able to characterize the response of that device, let's say just for temperature, to say, well, okay, it's cold outside, and then it got, a cold front moves in, so the temperature drops quickly. How long does it take for the temperature sensor inside that injection molded enclosure to notice that it got colder outside? There's going to be a lag time there. And then how are the the temperature sensors affected by the heat of the microprocessor on the board? So a lot of it's, like problem solving associated with, you have this goal, you design something, you prototype it, then you debug it. And what I do on a day-to-day basis, I do a lot of writing proposals. I do a lot of writing papers. I'm just kind of describing what we're doing, because a big part of my job is to go to federal agencies or companies and get their support for the project, because we don't work for free. All right, so that means proposals are always, there's always 1 or more proposals we're working on. There's always 1 or more papers with deadlines that we're working on. There's always another set of PowerPoint slides that describe what we're doing. And so, that I would say not everybody in the group that works for me would actually want to do the job I'm doing, because I like to write, I like to communicate, but I'm probably unusual in that respect. So most people that go into computer science would probably be very happy doing the kind of problem solving that you're doing when you're writing and creating something. And you kind of do it because, and I still do it because it's very satisfying when you come up against a problem and you figure it out. Even if somebody else has already figured it out, just the fact that you figured it out gives, that's one of the reasons why you kind of like to do, probably why you like to do software or design.
I have another question. So if someone wanted to apply for a job to work with you as a computer programmer, would there be specific languages they need to have knowledge of beforehand? If not, do you provide training or no?
I think so. That's a good question. I think we would look for people who've learned a couple of languages as evidence that they could learn another one. So as an example, I up until 5 years ago, I didn't know how to program in Python. I knew C++, C, Fortran, other things you might not have even heard of, right? Because they're old, right? But I didn't know Python, and it kind of bothered me that every time I wanted to change this one piece of software that I was running in my house, I had to ask one of our grad students to help. So I learned Python over the Christmas holidays, and over the course of 2 weeks, I probably spent 50 or 60 hours just learning Python. But at the end of the 2 weeks, I knew Python. So I say that because we would look for people who know how to do software, and then learning a new language is not trivial, but if you already have the concept of programming down, then we're less concerned about. So for example, if your resume said that you did these really cool projects in some language that we do no work in that language, and you said, but I know Python, I'm learning it, I'm doing a Coursera course on Python or something, then that would be a resume that would move higher in the stack than another one that said, I know Python and 6 other languages, that has unimpressive projects they did with Python. But the fact that you've done interesting projects is most important, more important than the actual language that you used. Having said that, we use a lot of R, we use a lot of Python, but I would say Python is the sort of universal. For our group, because we do hardware and software systems, we would also look for students that have some understanding of how to manage a Linux device. So if you came in and you just use a Mac or just use a Windows machine, then that'll be less impressive than if you came in and said, well, I have this Linux box that I manage, and I know how to program it. I know how to do system administration, to update the software, to do all my programming in the command line interface. That, for our group anyway, and I think for any group that does both hardware and software, that would also put you up further. And it's much more accessible these days, right? You can buy a Raspberry Pi Zero for $5 or a Raspberry Pi for $35, plug a keyboard and a network and a console into it, a TV into it, and so you can learn this even if you don't have any courses and that wasn't the case 20 years ago, but it is today. So I would recommend Python. I would recommend becoming skilled at managing a Linux box. Those are 2 things I would recommend.
Okay, thanks so much. Can we take a quick picture of you?
We have a
We have a little monitor, yeah, in the
big
front of
monitor
the
in
classroom.
front of me.
Can you hear you?
Can you hear us?
Oh.
Do you hear me? Hello?
Was that a question?
Oh, yeah, sorry. Can we take a quick picture with you? There's a little monitor in the front, so we're just gonna hop on.
Oh, you want to take a picture? Sure.
Yeah, okay. Let's go. That's for you.
It's okay.
Do you want to get a photo or no? Great.
No, go ahead.
Okay, 1.
Okay.
Don't you want to change this thing so that it's
Oh.
too small?
Yeah, no one's saying.
Can you say something real quick?
Could I say something real quick? Yes.
Oh, no.
Can you say something again?
Testing 1, 2, 3.
Okay, thank you very much.
Thank you.
Sure. No problem.
All right.
Can you use from here?
Yeah. Awesome. Thank you so much.
Wait, right here.
Thank you.
I might need the legend for you. Thank you.
Yeah, here it is.
Thank you.
Or, hey, look, if any of you guys want to send me email with more questions, feel free to do that. Just put something in the subject line, like with all caps saying, Del Norte High School question or something.
Okay.
All right?
And just be sure.
See you later.
And also just be sure we're allowed to post this on YouTube. Is that all right with you?
Oh, I'm sorry, what?
Are we allowed to post this on YouTube, this video?
Sure.
All right, perfect. Thank you so much. We'll see you later.
All right, see you later.
Bye.